Hello, and welcome to Earth Science Learning Online, where we now get to do our Earth Science for the next 2 weeks so that we don't get everybody sick. Before we get going on our lesson for the day, a couple things where this is our first lesson, just so you are aware, the plan, and you'll see it in the email I send out, and also it'll be on the Canvas course that you are now getting all this information from. But the plan is to basically have your set of lessons published and ready to go for you at the beginning of the week on Monday, and then all of that will be due by the end of the week. So all of the coursework for this week will be due basically by Sunday night, and then we'll start over again next week with our next set of materials. All right. You guys have lucked out to the point for the next 2 weeks. You don't have to see my face, but now you do still have to listen to my voice. We're going to try to make these notes go pretty quickly. But as we're going through them, on part of your Canvas course, you should also have a star life cycle diagram that you will need to have and be able to refer to throughout these notes. And I've also added on there a list of star vocab, and so make sure you have that and you're looking through that vocab list. Those words are going to be kind of our new important words as we start learning about stars and the cycles of stars. Okay, let's get into the life cycles of stars. Even though technically stars are not living, we still call them life cycles of stars because they have an event that creates them where they come into existence. So we call that the stars are born, and then they go through a set of steps until they go out of existence when we say they die. So it's called a life cycle. All right, so just to get into stars, we already know that stars, hopefully, are huge masses of gas, and they have this large gravitational pull because they're so big, and that's why we orbit around our sun. And then, as we talked about last week, through the process of nuclear fusion, they're giving them massive amounts of heat and light. And so it's this process of fusion that we've got to understand, because that's why stars evolve and change and have their life cycle. So we're going to go through the different steps of the star's life cycle. So in stage 1, it's going to start out as a nebula. And we're going to actually go into very big detail later on in this unit, going just from stage 1 to stage 2 and 3 in these notes. But we're going to keep it a little more simple today. So stage 1 is a nebula. The picture in the bottom corner is a picture of a nebula. But essentially, a nebula is this big cloud in space of gases and dust and particles. And from that, stars form. So for a star like our sun, we think our sun formed out of a nebula 4.6 billion years ago. And the whole reason our star begins to form is you have that cloud of gas and dust, and then there's forces, which we think now are probably static forces, cause particles to stick together, and then gravitational pull will slowly pull more of the materials towards the center through a more dense area. And then that gravitational pull is kind of the starting point of creating our star. All right, so that's stage 1, where we have our big cloud of gas and dust called a nebula. All right, and then stage 2 is our protostar stage. Proto meaning it's not the final form yet, like when you have a prototype of something, it's not the final stage of that thing. So same thing with a protostar. But where our protostar is would be the center of this cloud and gas and dust begins to condense and collapse due to gravity. And then as that gravity collapses it, the center and the friction and the forces going on there start to get it to become warmer. And then once there's enough pressure and heat in the core of our protostar, fusion's going to start happening. And then once fusion starts happening and we fuse hydrogen into helium, it becomes what we call a main sequence star. Excuse me. So a recap of what nuclear fusion is, as we talked just briefly about before we all got quarantined, is from that high temperature and large amounts of gravity, we're taking two smaller elements and combining them to make one larger element. Mostly when we're talking about this, we're going to be talking about hydrogen, the smallest element, element number 1, and turning it into helium, the second smallest element, element number 2. All right, so we have low mass stars like our sun are going to be converting hydrogen into helium. So if you look at those, the blue and red dots there represent two hydrogens, and then through heat and pressure, they're going to be squished together. And so like the blue is supposed to be a proton, the red is supposed to be an electron, and when you squish them together, you also add in a neutron there, but we're not going to go into exactly what's going on with that. You create a helium, and then our lightning bolt, which is representing the energy that is released when you do this process. And that energy that's released during this process, that lightning bolt, is the energy that we see coming from stars and from our own sun. That's the energy of the stars, is this energy of fusion. Okay. So now, what I want you to do, you're not going to talk with your neighbor because you no longer have a neighbor, but I want you to use the information below to determine what element is formed when two helium atoms combine. So look at the process that we just went through. 1 hydrogen plus 1 hydrogen equals 1 helium. And then now below there, we've got our periodic table. I want you to try and decide what 2 heliums will become. Okay, so on this, we can simplify it into pretty simple math. If we look at our periodic table, the atomic number is that number at the top, the only one that's on this picture. So like our hydrogen was a 1, our helium is a 2. So our equation above, hydrogen plus hydrogen equals 1 helium, then we're taking simply the atomic number 1 plus 1 equals 2. 2 is a helium, and so that's what it becomes. And so for our helium, if we combine 2 heliums together, you take a 2 plus 2 equals 4, so it becomes that Be, which is beryllium. So it's pretty basic math for our purposes and how fusion is going to work. You just take the atomic number at the top and you add them together, the 2 atoms combining, and then it creates the next one. Like if by some way we were able to fuse a hydrogen to a helium, you would take 1 plus 2, that would make us 3, which would be that Li, or lithium. So that's how fusion's working in the core of our stars. Okay, so now on to stage 3. We have a main sequence star. So when our protostar is going to reach this equilibrium, the equilibrium is reached because when fusion begins, it's going to be creating an outward force of all that energy trying to escape that is created during fusion. And so it starts to balance the collapse of gravity pushing down, and our star is going to reach this equilibrium. And so it'll be this main sequence star when the force of the energy escaping is equivalent to the force of the gravity pushing down, and our star will remain in that stable state for a very long time, just fusing hydrogen into helium. So at that point, there's only enough gravitational pressure to do the most simple form of fusion, which is hydrogen into helium. So like our sun is at that stage. Our sun is a main sequence star doing hydrogen to helium fusion. Eventually, though, that fusion is going to run out. The hydrogen will run out, and the fusion won't be possible anymore. So then we want to look at what's going to happen to our stars when the hydrogen runs out in the core. And that is going to be dependent upon how big your star is. So if you look at the diagram that is a part of this, you'll notice that it branches after a main sequence star. So it'll take one path for a star of a higher mass, and it'll take a second path for a star of a lower mass. And so depending on the size of your star, that'll change what is going to happen to that star. So we're going to follow the path of a star with a smaller mass. So like our sun is a smaller mass star. So this is what's going to happen to our star. So we're going to take, once fusion of hydrogen stops in the core, we lose that outward force of the energy trying to escape. And so gravity pushes down on the core more, and it actually starts to crush the core, but then it creates enough pressure that it starts to do higher fusion. So now it's going to start fusing helium and lithium and beryllium and boron. And for smaller mass stars, we really only do fusion up to about carbon. And once this is happening, as that core is collapsing more and more and more, then it's causing the star to expand and become a red giant. And so it's going to go from being a star the size of our sun to, when it becomes a red giant, it's going to expand to being about the size of Earth's orbit. So it's getting much, much bigger and a lot less dense. So it's going to cool off. When that happens, if the sun expands to the size of our orbit, then Earth's in trouble, because it'll suddenly be right where our sun is, and so Earth's going to get toasted. But don't worry, that's still about 5 billion years away, so not a problem to worry about for you yet. Okay, and then once it's a red giant, oh wait, before we get there, here's our picture. So the yellow dot on the left is the size of our sun right now, and then when our sun begins to run out of fuel and expands into a red giant, then the big red circle is the size that our sun will become. All right, and then once it can no longer do fusion, the gravitational forces of everything around it will completely collapse the core. Fusion will cease, and then we'll create what we call a planetary nebula, where the outer parts of the star escape out into space. And so we no longer have like a star that's doing fusion. But if you look in the middle of this picture, there's a white dot right in the center of that picture. And that white dot is the core of the star that created this planetary nebula. So all the outer parts of that star have escaped into space and created a new nebula, like what we talked about at the beginning of these notes. And now at the center, we have that essentially hot, white, glowing core that's no longer doing fusion, but it's so dense and so hot, it's going to be glowing still for billions of years. And that white dot that's there is what we call a white dwarf. So once our red giant uses up all its fuel, we have that hot, dense core left behind that is a white dwarf. And then theoretically, once it cools off, because it will cool off eventually because there's no more energy being added to it, it will become what we call a black dwarf, although we don't think the universe has existed long enough yet for black dwarfs to exist. And even if they did exist, we wouldn't be able to see them because they're no longer emitting light. For a small mass star, this is an important part. This whole life cycle is a very long life cycle. It takes about 10 billion years which we think our sun's about 4.6 billion years. So we assume that our sun's only is still less than halfway through its complete life cycle. Okay, and now we're going to follow that other branching pathway and see what happens when you have a large mass star that begins to die. And this one, for a lot of purposes, is a much more exciting ending. Oh, but before we do that, that's the size comparison. So when the core of your star collapses, it crushes it so small that a white dwarf is only about the size of the Earth. So if you think about the total size of the sun, and that core gets crushed down to something the size of the Earth, so it's super dense and really hot, so it'll be glowing for a long time. Okay, now our stars with a large mass. So a similar idea, but so large stars begin to run out of fuel a lot quicker. So even though there's more fuel in the core because there's a higher mass, there's so much pressure that the fusion happens a lot faster, and the stars run out of fuel very quickly. And then same thing will start to happen as they run out of hydrogen. Then it's going to begin to expand. So it expands to what we call a red supergiant. And they expand and cool because they're becoming less dense. And then it's still going to do the same process where it's going to take, it's going to run out, and so the core will collapse a little bit, and then it'll start fusing bigger elements, and then it'll collapse a little bit more, and it'll create more pressure to fuse bigger and bigger elements. Except for in our large mass stars, we go beyond carbon and nitrogen and oxygens, which are numbers 6, 7, and 8, and it can fuse bigger and bigger and bigger elements up until element number 26, which is iron. And then after fusion of iron happens in the core of our star, that's basically the final death sentence of that star. Fusion won't happen larger than iron inside the cores of these stars. And so once iron is fused, it's basically a matter of basically moments in the life cycle of a star, and that star will undergo a supernova, where basically that core collapses super intensely, and then the whole star explodes. And so these red supergiants are running out of the fuel, and their core is collapsing, and then the final collapse after iron will blow off all of the outer layers into space in this explosion we call a supernova. A supernova and the extremely massive stars, our high mass stars, actually go even bigger, and we call them now a hypernova. These are the most energetic things we can see in the universe. They are, to us now, other than when the Big Bang happened, it is the most energetic thing that happens in our universe and could be extremely destructive. I mean, it's an explosion that in the lifetime of the star, it happens in mere moments, but in real time, it's an explosion that can last for weeks. So the star is exploding for weeks. So here's our size comparisons there. So if you look at the little yellow dot in the top right, that's the size of our sun. And then the circle below it, the red giant, is what our sun will become. But then if you look at the big red circle on the left, that would be the size of red supergiants that exist out there. Okay. This picture is a picture of a nebula that happened after a supernova. You might be able to guess the name of this nebula based on the shape. We call it the Hourglass Nebula. But this nebula gives us a good idea of what's happening with the supernova, because you can actually see where that star exploded and basically shot out its stuff in two directions into space, creating that hourglass nebula shape. All right, and then this picture here is a picture of a supernova that is happening. So the picture actually on the right with the arrow is before the star exploded. So that star it's pointing to is the star before the supernova, and then the star on the left is what that star looked like when the supernova was happening. This is actually a very important picture in science. It was taken in 1987, if I remember right. It was the first time a supernova had ever actually been recorded. So before that, supernovas had been theorized and they were hypothetical, but this was the first time scientists actually saw a supernova occurring. And so you can see that picture on the left, how much brighter that star becomes when the supernova is happening. In fact, when you see a supernova happening in a distant galaxy, it can create so much light and so much energy that it actually washes out all the other light of all the billions of stars in that galaxy, and all you see is the light from the one star that's exploding, and you don't see any more of the light from the other billions of stars that exist in that galaxy. Okay, and then our high mass stars will branch again based on size once more. So if you had a smaller high mass star, it won't collapse the core as intensely, but still pretty intensely, and it creates what we call a neutron star. Our neutron stars are actually some of the craziest things that exist out there in the universe. Like there's one called a magnetar that's like super intense magnetic material, and it's so dense and so strong that it would have enough magnetic force to be able to pull the iron out of your blood from thousands of miles away. And so they're like that strongly magnetic. And then our supermassive stars that go hypernova, they crush the core so intensely that it basically creates such a density in the core, like that it starts to pull all the other material into it because it has such a high gravitational pull because of the extreme density. And so it begins to pull all the other stuff of that star into it, and it creates a black hole. And so these black holes then are created during these hypernovas. And the big key with these larger stars is their lifespans are much, much shorter. Where our small mass stars might exist for up to 5 billion years, these high mass stars are only around for about 5 million years. So much, much shorter time period. They won't exist nearly as long. Okay, well, that's not what I wanted to do. All right, so this is similar to the diagram that you have on Canvas that you hopefully are looking at or printed out. So if we just look at, these are the steps of our high mass star, right? So we started a protostar, then we go to our main sequence, supergiant, so on and so forth. And then same thing with our low mass stars. You will need a copy of this diagram or a copy of these notes up for the assignment that you are going to be working on with star life cycles to be able to complete it. And then that is where we are going to stop these notes for today. Have a good day, everybody. We'll hopefully see you in a couple of weeks.